Welcome back, everybody. This is going to be video 2 of 3, looking at significant figures and the calculations with significant figures. For this video in particular, we're going to take a look at multiplication and division calculations. The general rule with this is that you're going to round your answer to the same number of significant figures as the measurement with the fewest significant figures. Now, this seems kind of arbitrary and may not understand what's happening quite with it just yet. We're going to kind of revisit it and unpack it in just a little bit. And I want you to keep it in the back of your mind as we take a look at this first question here. If I had a rectangle, either a carpet square or a box, something to that effect, with one side that's about 2 meters and another side that's about 3.1 meters, what would be the area of this box? If this was math class, you would just do 3.1 meters times 2 meters, and you would get 6.2 meters. And in math class, that would be correct, but in science class, this is actually not going to be good. Reasoning behind this is the same thing that we were talking about in the previous video. The fact that when we say about 2 meters, we're talking about an estimation is being made in the ones place for this measurement. And when we say about 3.1 meters, an estimation is being made in the tenths place for this one. So because we make estimations in different points, and because we make any estimation overall, we can't simply just take all of the numbers that result from this calculation and assume that they're correct. Now, why is this? Let's kind of look at this from a measurement perspective. If I handed you this carpet square and you came back to me and said that it was about 3.1 meters wide, what this means to me, and if I think about this, I can kind of break this down into what this measurement means. 3.1 meters, again, means that your estimation took place at the tenths spot, to the tenth of a meter. And so anything greater than 3.1 up to about 3.14 meters would round down to 3.1. And anything below 3.1, cutting off at 3.05 meters, would round up to 3.1. So we have this kind of range of numbers here, this rough range of numbers, that all could give us this measurement of 3.1 meters. For 2 meters, we can kind of think through the same thought process. For 2 meters, if you came back and told me that something is about 2 meters that you rounded to the nearest meter, not only am I going to think that you're extremely lazy, because there's no instrument that we have in this class that's going to give you an estimation point to the nearest meter, but that's besides the point. This means to me that this could be somewhere between 2.4 meters at its rough maximum and 1.5 meters at its rough minimum. And really, it could be any number in between these two values and still give us a rounded to the nearest meter number for 2 meters. So instead of thinking of this like 2 meters and 3.1 meters multiplied together to give us an area, I almost want you to think of it as a range of values that we're trying to multiply together to give us a rough area. So instead, I'm gonna pull a couple numbers out to give us an idea of what we're looking at here. I'm going to take the top two values. I'm going to take 3.14 and 2.4 and multiply those guys together. And this is going to give me a rather large number, 7.536. And I'm going to do the same thing for my bottom values here. I'm going to take 3.05 and 1.5. And again, multiply these numbers together to get some value. So what we kind of have here is the upper and lower limit to what our calculation could be here. If we had the absolute max, it's going to be about 7.536. If we had the absolute minimum for what these values could be, it could be 4.575. Now, because this is such a huge array of numbers here, we don't have very much certainty about this number. Now, because we have this 7.5 and this 4.5, we can't give a number that is more certain than we are about this. Because our ones values don't agree with each other in the upper bound or the lower bound, that means that this is where our estimation is going to take place. And so now we're going to pick a number that is somewhere between 7.536 and 4.575. That's rounded to that ones place. And if we looked at between 4.5 and 7.5 on a number line, almost smack dab in the center is going to be this number 6. And so because we don't have a good idea of what should be in the ones place in either of these numbers, we definitely are not going to have a good idea of what's in the tenths, hundredths, or thousandths place either. So we're going to make one estimation for this number here, and we're only going to have one significant figure. So because this comes roughly in between for 6, our final answer here is going to be about 6 meters. And it's all based off of how much uncertainty there was in your numbered values, how much variation there is in this range of what this answer could be based off of the numbers that were given from the measurements. Now, this seems like a pretty complicated process. You could repeat this for every single time you do a value to try and find common values and then figure out where the rounding has to take place. But there's a much easier way to do it. Instead, we just need to look at the number of significant figures in each of these values. So we have 3.1, a number that we were sure about, and where our estimation took place, and 2 meters, where the 2 is where the estimation took place, for 2 sig figs and 1 sig fig. Now, because we only had one significant figure in this value here, we can't do any estimation past that first significant figure. That's really what this calculation here is telling us, is that we are only one significant figure sure about this final answer. So that's why when we multiply these together, we do 3.1 times 2, which would give us 6.2, but we round to the lowest number of significant figures, where our 2 had one significant figure, so we're going to round to that first significant figure here, and 6.2 is going to round to give us 6. So this whole big process here, figuring these kind of like ranges out, not really necessary if we just go off of how many significant figures each number has. And it's a really good approximation in like 99% cases. And in those kind of fringe cases, we're not really going to worry about. So let's take a look at some more examples of these significant figure calculations for multiplication and division. And it works the same way for both multiplication and division. I have 3 examples here. I'll go through these 3 examples. Again, just like the previous video, if you want to pause and try these out for yourself first, I'll give a quick pause here to let you pause the video, try them out for yourself. So for the first example here, we have 34.3 centimeters times 2.7 centimeters. When we multiply these two numbers together, we're going to get 92.61 centimeters squared before we do any rounding. Now we have our number. Let's check our significant figures. In the first number here, 34.3, we have 3 significant figures, 2 numbers that we were sure about, and our 1 estimation for 3 Sig Fig 3 SF. In 2.7, same deal. We have 1 number that we were sure about, and our estimation in the 10th place for 2 Sig Figs. So since we're only 2 significant figures sure about this number, we can only be 2 significant figures sure about this answer. So I'm going to find my second significant figure here. So starting from the left side, I have a number that we're going to be sure about and a number that we're going to be doing some rounding with. So I'm going to take 92.61 and round to the nearest 10th spot, nearest ones place, excuse me, and I'm going to get 93 centimeters squared. For the second problem here, we have 3 different values, but it's done the same exact way as before. We multiply these numbers together. I'm going to get 7,960.437 millimeters cubed. I'm going to take a look at these significant figures for each of these values here. We have sure about, estimation for 4 significant figures. Sure, estimation, 3. Sure about, and our estimation for 2. So because the lowest number of sig figures that we have in this multiplication is 2, that means that we can only have 2 significant figures in our final answer. So we're sure about the first value. We're going to round to the second value to have 2 significant figures here. And this would give us 8,000 millimeters cubed. Now, again, if you handed somebody this measurement, they wouldn't necessarily be sure where your rounding took place. So again, there's a couple different ways that you can make a note of this. If you put a bar over the top of your estimated digit, you let them know where the rounding took place. So right here, my reader knows that I rounded to the hundreds place if I put the bar over the top. Or you can put this into scientific notation and just keep those zeros at the end to show where the rounding took place. So 8,000 millimeters cubed would turn into 8.0 times 10 to the 3rd millimeters cubed. And for our last value here, we have 22.667 milliliters, 23.49 milliliters. This is going to come out to 0.9649638, and it's going to keep going. This is a repeating decimal, does not repeat ever. And same thing as we did above, even though it's division, it works off of the same rule. We count up the significant figures in each of these numbers. So 22.667 is going to have 5 significant figures, and 23.49 is going to have 4 significant figures. which means that we're 4 numbers short about our final answer, so we should round to 4 significant figures. So finding our 4th significant figure here, starting from the left side with the Pacific rule. And our final answer is going to be 0.964. And then this estimation here, when we round to the nearest 10,000th place, the 6 is going to round up. So instead of this being 964, this is going to be 965. And to show that this rounding took place at that 10,000 spot, we're going to leave that 0 there at the end. Hope this makes sense. If you have any questions, guys, please talk to me in class, talk to me outside of class, preferably, because again, we're not going to have too much time to talk about this stuff outside of the first week. And if you don't know what's going on with this, you're going to have a tough time. So please let me know if you have any questions moving forward. Thanks for watching.